Okay, hello everyone. Welcome to Linear Integrated Circuit and Design lecture number 1. So today's topic of discussion will be Opamp abstraction, Opamp symbol and circuit model, ideal Opamp properties, and Opamp characteristics overview. So let us directly start with the topic. So first we will see what do you mean by Opamp. So basically, OPAMP stands for operational amplifier. The name is operational amplifier due to the fact that it can perform all the mathematical operations like addition, subtraction, multiplication, integration, differentiation. So that's why the name operational amplifier. It's really a cool device because using OPAMP you can build many useful circuits, and it's a workhorse of analog industry, mostly used there. So now let us understand what do you mean by the word Opamp abstraction. So instead of explaining you directly, I will give you some real life examples where you can relate to this topic very easily. So let us start. So first, let us consider an example of a food processor. Or we can mix vegetables, or make juices and all that. That's automatically, in the normal language, it's also called as a mixer. So how does it look like? So basically it's like a jar kind of a shape, and you have a processor operating buttons here, and you can feed in the stuff from here to mix it down. So this is basically what you mean by a food processor. So what's the example? Why I'm giving you this example is the reason is very simple. Food processor, you know the interface, you know how to use it. You have to turn on the processor, turn off the processor, increase the speed from 1 to 3 different speeds are given, but you don't know what's really going on inside the food processor. You don't know the electronics inside it, basically. So that's what the point over here is. You know how to use it, but you don't know how does it work. Next example is, I can want to share is example of a car. So let's list it down for a car. Let's list it. There's the number of things which we know about it and number of things which we don't know about it. So no. So what's the first thing we know about the car? We know to how to drive it, right? We know how to drive a car. Secondly, we know how the steering wheel works. So how the steering wheel works. Thirdly, we know how the brake pedal works. Whoever takes a driving lesson has goes through these steps. So we know how the brake pedal works, and we also know how the accelerator works. In order to increase the speed of the car, so you have to press the gas pedal basically, right? And we know other things also, much how to utilize the car optimally, right? So basically these all are interfaces, right? And what we don't know about the car is, we don't know how does the engine works. So let me just write it over here. So So what do we don't know about the car? How does it work? So what's really going on inside the engine? How does the gearbox work? Right? So these things, we even in spite of not knowing them, still it is easier and we are quite comfortable driving a car, right? Without worrying, how does the engine will work, how does the gearbox ratio will work, all these things. Still, we are comfortable driving this car, right? Similarly, is the case of an Opamp. So let's say Opamp is like a black box. So this black box has some inputs and it gives some output. So we are not interested inside what's inside this black box. So basically, it can be a mystery. We don't know how does it work, what all inside transistors are there, but we are comfortable using this op-amp. So that's what the abstraction means. We really don't know how does that thing works, but we can use that, that device or that component really to make something useful. So learn to work with abstractions without really knowing what's inside. So that's what an abstraction means. Okay, so let us move on to the next topic now. We'll go to now the Opamp symbol. So let's consider next topic as, let me just Opamp symbol. Okay, just let me check. Yeah, it's fine. So for the Opamp symbol, it's looking like this. Opamp is represented by this triangle. It has an input port, a power supply port, and an output port, which is measured with respect to ground again. So this, let me just take a different color and show you how does it connected from the outside world. So here I have you know a DC supply. Again, I have a DC supply connected to this. This is normally termed as VCC. This is termed as VEE, and this is common ground. Okay, so these are my two inputs. Also, we can write it as V minus and V plus. So now let me write different ports available over here. So this is my input port. That's my power port, and this is my output. So that's how the Opamp symbol looks like. We can make it even more simpler and more clear and more abstract representation of the symbol we can call it. So this can be drawn again as follows. So again you have this Opamp plus minus plus, we can call it, doesn't matter. This is called as V minus, this is called as V plus, and you have your power supply port. No need to show it again and again. It's understood that it's connected to minus and plus power supplies. And there is my output, plus, minus, V out. So this is my normal, a more simpler and a clearer symbol of a op-amp. So let me just write over here, op-amp symbol. So this is more abstract representation of a op-amp symbol. Also, one more thing you notice that the input is not single-ended in case of op-amp. It is, differential input. Like you must have heard of this term in differential amplifier. So here your input is differential input. It's good to know. This will come in handy. Basically, a differential amplifier is the first stage inside the op-amp. Okay, so after knowing this, we should come back to the abstraction. So, what do you mean by abstraction? Uh, it's very easy to design with op-amps. You will be shocked to know how simple it is to design many applications using op-amp without really knowing what's going inside the op-amp. So that's the meaning of the word op-amp abstraction. Okay, so we move on to the next topic now. So the next topic is circuit model of op-amp. Oh, sorry. So let us, discuss this topic over here. I will write it down over here. Circuit. Oh, it's a bigger one. Okay. Circuit model of op-amp. Remember, this is ideal case. Okay. So practical circuit will have a slightly different, the diagram. Now let me quickly draw a op-amp. So op-amp consists of two input terminals, V minus V plus, output terminal, V out, plus minus, and with respect to ground. It's understood, no need to show VCC V every time, but it's understood. Uh, okay, so I am drawing now. We are going to see how does the circuit model of a op-amp looks like. So now let me take my pen again and let us start drawing it. At the input side, it looks something like this. It has two wires. This is V plus and this is V minus. And the difference between the both is called as differential voltage VD. And at the output side, we have plus minus. It is A times VD. It is basically a voltage dependent source, dependent voltage source we can call it. And here is my output, V out plus minus, and this is with respect to ground, and this is also grounded basically. So this is my circuit model of op-amp, an ideal op-amp. Basically, we will learn many things from here also. So it will give you information about the ideal characteristics of op-amp. So here, since both the terminals are not connected, are open basically. So here we can call it as the current flowing to this terminal is is almost zero. So this is, let's say, V plus is zero, and here I minus is also zero. So no current flowing is flowing into the input terminals of op-amp. What does that mean? That the op-amp itself doesn't take any current, and that means it has very high input impedance. That's a very good advantage. Also at the output side, we don't have any impedance, so it has around zero output impedance. That's one few of the ideal op-amp properties. And this VD, let us explore this VD. VD is called as differential input voltage. So VD is given by V plus minus V minus. And how do you define VD? VD is nothing but the voltage difference between, oh, this is not so clear. Yeah. So voltage difference between two input terminals. So basically I can write voltage difference between two input terminals. So that's what VD means. And from this output relation, we can write V out is equal to A times VD. So let us do that. Let me again change the color of my pen and take somewhat around green. Okay, so V out is given by A times VD. And what is VD given by? VD is given by V plus minus V minus, which is nothing but the difference between the two inputs. So basically, it's quite similar to what we have studied for a differential amplifier. In a differential amplifier, amplifies the difference between the two inputs, and operational amplifier is also doing the same. So basically, we can say V out is proportional to V plus minus V minus. So it amplifies the difference between the two input terminals. Now there are few Opamp, ideal Opamp properties which you can make out from this circuit model of Opamp. First is very high input impedance. Second is very low output impedance, that is zero. And the life doesn't get anything better than this, because if we have a infinite input resistance and zero output resistance, that's ideal case. And one more thing we have is the gain of this amplifier. The ideal amplifier is extremely high, so basically infinite. So the gain of op-amp is infinite in the ideal case. So that's a big advantage. So it's virtually infinite. Now, next we will see is the comparison between ideal op-amp 741 and integrated circuit op-amp. So modern integrated op-amp we will see. So let us. I will write down the comparison. I will write down the comparison just to save time. Okay, so you can see the comparison between the three. So first we have is the ideal op-amp. Next is IC741, which we'll be using it throughout the subject. That is the commercial IC which is available, and the model integrated circuits. Model integrated op-amp. So first we'll see the comparison for the gain. For ideal op-amp it is infinite. For 741 it is around 10 raised to 5 to 10 raised to 6. And for model integrated circuits it's around 50 to 100. And the input impedance for ideal op-amp is again infinite. For 741 it's around several megahertz, and for modern integrated circuits it's around, it's not hertz, let me correct it. What happened? Okay, it's basically ohms, not hertz. Yeah, so input impedance is several mega ohms for both 741 and modern integrated op-amp. Output impedance for ideal is around 0. For 741 it's around 100 ohms, and for output impedance is around few kilo ohms. Speed, which is very important, which is the measure of how fast the op-amp is. So for ideal op-amp the bandwidth is around infinite, and for 741 it's around 1.5 megahertz, and that's the most important feature in modern integrated op-amp is around uh, several gigahertz. Power dissipation in ideal op-amp is 0. For 741 it's around 80 milliwatt, and for modern integrated op-amp it's around 5 to 10 milliwatt, and the cost is around 0 for ideal op-amp. It's very negligible. For 741 it's less than around 50 rupees, and for the modern integrated circuit, since we are integrating many op-amps into one chip, its cost is less than 0.1 rupee. So this is the ideal op-amp properties in comparison with 741 and modern integrated op-amp. Now we'll move on to the next topic. So our next topic will be Opamp characteristics overview. We will just go through this topic in a very glance view. So Opamp, oh sorry, let me just write it over here. Yeah, that's fine. So Opamp characteristics overview. So we are not going to go into details, but whatever useful information we require, we'll gather from here. So basically, we have seen Opamp. How does it look like by now? So Opamp, it's having two input terminals and two power ports and one output terminal. And if I connect a load over here, oh, wait a minute. Yeah. So if I connect a resistive load over here, I can measure the output with respect to load. And these are my power connections. This is VCC and this is minus VE, and this we can call it as a minus plus. And the gain of the op-amp is around, we can call it as A. So A is the gain of the op-amp and these are my inputs. I can call it as Vi. So this way the op-amp is connected in open loop mode. That means its input are just open circuit. So in such a case, we have found out that for 741, the A is around 10 raised to 6 to 10 raised to 5. And for ideal op-amp, it's about infinite. So what we can say over here is, we know that the output expression for op-amp is given by A times B plus minus B minus. So what does that mean? What does this number mean to us? That's 10 raised to 6. That means the following. So if this is around 10 raised to 6, and let's say we want output of around 1 volt, so how much should be this difference? The difference between V plus and V minus has to be 10 raised to minus 6, which is impossible. It cannot have so less difference, which is possible basically, but not realizable. Okay, unreliable basically, we can call it. Getting such rare combination of so much less difference in the inputs, it's very rare. So basically we don't follow this approach. We use op-amp in closed loop configuration, and let's try to plot the characteristics now for the op-amp. So the characteristics of the op-amp will be something like this. So on the x-axis we have differential inputs. So here is my V plus and V minus is my differential input, and this is my output. So earlier I have said that the difference between V plus and V minus cannot be 10 raised to minus 6. It's impossible. It's possible in case of biomedical signals whose amplitude is around microvolts range, but it's not it's not recommended to use op-amp in open loop configuration because of the following features, disadvantages. Now let's go to the characteristics. Now I'll just plot it without explaining much. So that's how the characteristics will look like. This will be close to around few microvolts, let's say 10 microvolt. This also will be around plus 10 microvolt basically. Let me use a eraser. Okay, so this will be around 10 microvolt. So what we are saying over here is the op-amp will be linear as long as the difference between the input falls within this range, that is plus 10 microvolt to minus 10 microvolt, and outside that it will hit a rail. So what is this? This is around 12 volts rail, and this is plus 12 volts rail. So what does it mean is if the difference between the input is greater than 10 microvolt or greater than minus 10 microvolt or less than 10 minus 10 microvolt, then what will happen is the op-amp will operate in the saturation. Op-amp will enter the saturation. So your op-amp saturates. So how does this happen? The op-amp is in saturation because the output hits allowed, the maximum value allowed by the power supply. So you have to be very, very careful. So even in this formula, we can see that even a small change in the input can trigger the op-amp to, either to positive power supply rail or a negative power supply rail. So this is what the characteristics look like. So what can we say about this gain, open loop gain? It's around 10 is to 6. That means it's very high. It's unstable, unreliable also, and it's basically also one more factor coming into picture. It's temperature dependent. So when it is temperature dependent, that means the gain will change with temperature. So it's not a good choice. So hence, due to all these things, this is basically open loop. When op-amp is in open loop. So whenever the op-amp is in open loop, it is not of much use for us right now for linear applications basically. It has some applications in open loop configuration also, but we will see that later. So right now, we have covered this characteristics for op-amp. So this will just show the op-amp in the open loop configuration. And the region between, one more thing I forgot, the region between this plus 10 microvolt and minus 10 microvolt is called as the active region for the for the op-amp to work in the linear range. So we have come to the end of our lecture. So today's topic which we have discussed were op-amp abstraction. So we have seen that why op-amp abstraction is useful and why without knowing the working of an op-amp, how it will be very, very useful in building up very useful circuits. Then next we have seen op-amp symbol and the circuit model. Then we have seen ideal op-amp properties and we have seen its comparison between the 741 and modern integrated op-amp. And lastly, we have seen just given an overview of Opamp characteristics in open loop configuration. So that's it for this LICD lecture number 1. See you next time.